Hi, ladies and gentlemen. We have moved on to section 2.2 in the textbook. We're going to talk about how we can use the 64-bit representation that we have inherent with double precision arithmetic. So starting in, we have the conversation about machine precision. We've already discussed this in class, so this is somewhat of a review for you. This is the number that I showed you in class. We have our 52 bits in the mantissa, which allow us this degree of precision in our numbers. There's some conversation in here about numbers that the computer cannot differentiate. I'll let you take a look at that. And what we're going to start with is this example here. And you can skip the display. That is an exercise for a different type of problem. But what I'm going to do is I'm going to pull up MATLAB code, which is set to do something that's very similar to this. So over here, let me just orient you to what I have. I'm going to set x equal to 0. I'm going to define, instead of leaving this as 0.1, I'm going to define a change in x value. In this case, it's going to be 1/8. And what we're going to do is run the same while loop. While x is not equal to 1, then x is going to be equal to x plus the dx, plus the delta x. And then we'll print out what we have for x and for 1 minus x. And so we can see what's going to happen. So x starts as 0, and the first time through the loop it's going to add 1/8, and then the second time through it's going to add 1/8, and the third time through it's going to add 1/8, and it's going to run through the loop 8 times, at which point x will be equal to 1, and we will break out of the situation. So this is a section. Let me run the section, and we'll see what happens. I'll pull up the MATLAB side over here, run the section, and we have the output exactly as we suspect. So what we have, let me move this over a little bit so we can see a little bit more of the output. We have the 1/8, 1/4, 3/8, 1/2, etc. on our way up to 1, and then the program stops. So in the textbook, the example says, well, we should try with 1/10. And so when we do that, we'll change this. Instead of 1/8, we'll make this 1/10, and we'll rerun the section. And when we do, what we see is the program does not stop because the x value is never actually equal to 1. The machine cannot represent 1/10 exactly. It has to round off because 1/10 is not a power of 2. It's not a binary number. So the machine does the best that it can to represent 1/10, but it can't actually represent it. So it adds 1/10, 2/10, 3/10. You already see down here the error accumulating as it progresses through the summation of 1/10. And finally, we get to this spot here where x should be equal to 1, but it isn't. We have error down in the last 3 digits of the number. And we can see the 1 minus x, which should be equal to 0 at this point, has these 1s down here. So the while loop does not stop. The while loop just continues on because the condition has not been satisfied. Now I've used the program here to stop once x exceeds 2. But what this does is it highlights the fact that we have to use numbers whenever possible that the machine can represent exactly in order to minimize the error. So I have a program here which is decimal to binary, and it will give us the binary for 0.1. So if I run this, what we have, and now I have to open up MATLAB a little bit more, this here is the actual 64-bit word for 1/10, at least as close as the machine can get. It isn't exact. It's done the best it can, but it only has 52 bits of precision, and so it has an error. Let me show you a different one for comparison's sake. What if we did the 1/8? So what if we take 1/8 and we represent that in binary? So the binary representation for 1/8 is exact. We have exactly the number we want. So we have the exponent set to -3. And so because we have the exponent set to -3, then that's going to give us 2 to the -3rd, which is what 1/8 is equal to. In fact, there is no precision data because 1/8 is an exact number in the machine. Every power of 2 is this way. So anytime we run loops, anytime we're going to do things over and over and over again, we always want to use powers of 2 in order to minimize the amount of error that we generate. Let's go back to the book. So this exercise and the discussion that follows is exactly what we just discussed. Here's the conversation about underflow. The smallest number that the machine can represent that's not equal to 0 is represented here. We have one lone 1 down here in the very last precision bit. And then we have overflow conversation as well. I want you to read all of that. That's not the point of anything new. You've seen that before. What I want to focus on is this conversation here. How do we solve this function for values of x and y? Let's think for a minute. If we have a value of x, which is greater than 2 to the 512th power, when we square that, we will have 2 to the 1024th power, and that will give us infinity. So we won't be able to do this calculation for numbers that exceed 2 to the 511th power. We can rewrite this function in a piecewise manner that resolves this issue for us. So what this does, and I just want to tear this apart for us, what this does is it says if x in magnitude is less than y, what we're going to do is we're going to factor what we have up here into a different form. Let me show you how that works. Here are the couple of steps of algebra that gets us to where we're headed. Let's say we factor x squared out of both of these numbers. We do that and we have this interim step, and then the result is when we pull the x squared square root outside, what that gives us is the magnitude of x. So the absolute value of x multiplied times this square root is equivalent to the original function. And that's all we've done here. We've built two different versions of this so that we're always dividing by the larger number. Just like we did with Gaussian elimination and partial pivoting, we always want to divide by the largest number that we have if we have a choice. So we compare the magnitude of x and magnitude of y. When the magnitude of y is larger, we divide by that. When the magnitude of x is larger, we divide by that. And the result is we can actually do computations for exactly the same function, but for all of the values that the computer can hold, not just some of them. Let me show you. So here I've built the two functions. Over here on the left-hand side in the MATLAB main window, I have the function as defined in the textbook, the square root of x squared plus y squared. I can build this as an inline, or what is now called an anonymous function. It's called anonymous because we have not actually built the function using a function script. So I can enter that function in. On this side, to build the piecewise function, I actually have to use a function script. If you come up underneath new here, and let me turn on my magnifier. If you come up underneath new and you can select script or live script. I know some of you have been using live scripts, although when we get to heavy computation, the live script is not very effective. The next option down is function. When you select function, what it does is it opens up a new function outline. So the command is function and it requires an end. And then what it has is it has whatever outputs that you might want. In our case, we only have one output. And then it has the name of the function, and then it takes in whatever inputs. Whatever your first comment block is here will actually show up when you type help. And then there's whatever you're putting inside of your function. So let me show you what that function looks like for us. Here I have function. This is the end down here that goes with the function. And what we have is output. I have very unoriginally called the output. And the name of the function is stable. and it takes in two values, x and y. And so what it does is exactly what we discussed in the book. It just asks whether x or y is larger in magnitude and then gives the appropriate function. So what we want to do is we want to test out both of these things. And what I'm going to do is I'm going to build a loop. So I'm going to loop from 1 to 1024. This is a very common way for us to test functions or anything else when we want to use large or small numbers. So I'm going to go from 1 to 1024, and I'm going to have my output, except I shouldn't call it that, so I'll call it my test output, is going to be f, and my x value, I'm going to set that as 2 to the k, and my y value is going to be 2 to the k. And you could argue that perhaps I should be doing some randomization in here, and that's probably true. But you can do that if you'd like. And then I'm also going to call stable, which is my stable function defined over here. And I'm going to set that up for the same inputs for x and for y. And what we'll do is we will just run through from 1 to 1024. Notice that we will be raising 2 to these powers, and that will give us a full stretch on the top end of the numbers that the machine can hold. And I have an error. So let me see what I have. I don't have my parentheses here. And the stable function it doesn't recognize, so let me run it once. It's not in the path, so now it's in the path. Now when I run it, everything should be fine. So let me maximize this and run it again. And what we see is, unsurprisingly, our test output, when we have the regular function of f is equal to the square root of x squared plus y squared, when the x squared and y squared terms become too large, then it generates infinity. So if either the x or the y reaches, remember the maximum end of the computation is 10 to the 308th power, so as soon as we get around 10 to the 154th power, which is right where we are, we square that number and it gives us an overflow error, which MATLAB shows us as infinity. The other version, because I'm dividing by the larger number and just multiplying by the magnitude of that largest number, then you can see this carries on and gives me all of the output exactly as it should, all the way up until the machine runs out of precision or runs out of magnitude. So this last number is the maximum number. Down here we have not a number. This is the maximum number for our computation. This is part of what you need to be able to do. When I told you originally that we were going to look at not only being able to program the computer to have it do what we want it to do, but also be able to put pencil to paper and do the calculations, this is what I'm talking about. Given the function square root of x squared plus y squared, we need to go and do some algebra to manipulate that function and rewrite it in a way in which the machine can use it more effectively. All right, let's go back and take a look at the text. So then what we have left are the exercises. So section 2.3, we are going to skip in its entirety. We're not going to talk about forward and backward error analysis. They're not discussed anywhere else in the text, and this is really introductory material for the potential of going to graduate school. So we can do without this section, and we will not discuss it. What we'll do next is talk about section 2.4.